Now we have another sorting algorithm, radix sort. So here's the question. Okay, let's assume that we have a shuffled deck of cards. So in the deck we have 52 cards, and we have 4 shapes like diamond, heart, clover, and spade. And then each shape has 12 cards. Okay, then if it is shuffled, the cards are shuffled, then how would you sort their cards? Think about it. So are you gonna use maxip? Are you gonna use quick sort, insertion sort, bubble sort? Okay, so usually we don't use any of the previous sorting algorithms. More likely, you're gonna use a radix sort kind of approach. Okay, so think about the deck of cards. Okay, so if we have a shuffled 52 cards, then probably lots of people try this approach. First, categorize the cards into 4 shapes. Okay, so linearly we can actually distribute the cards into 4 classes. Okay, when I look at one card, if it is a diamond, then I'll put it in the diamond category, and if it is spade, then I'll put that card in the spade, and clover and heart. Okay, so now I have four categories, and each category has 12 cards. Okay, so in the 12 in the category, then I'm going to apply some sorting algorithm. Okay, so what did I do? Okay, so I used the kind of memory space to categorize first based on this shape. So shape is kind of one feature of these keys. Okay, the cards have 2 keys, right? So the shape and the numbers, including K, Q, J. Okay, so we have a number and we have a shape, and I use the shape first. Okay, and then I sort the numbers in the shape. Okay, so this is kind of the basic idea of radix sort. So key is composed of k digits. Think about 3 numbers in this example, 3, 2, 9. This is one key, but when we look at this key, then we have 3 digits, right? 3, 2, 9. Okay, and if it is a decimal number, then it looks like this. And each digit is one of 10 numbers, right, from 0 to 9. If it is binary number, like 0, 1, 1, 1, 0 or something, then in this case, each digit could be either of 0 or 1. This is why we call it binary number. Okay, so decimal number has 10 choices. Okay, so in a card we have shape and number, and we have 4 possible options for shape, and we have 12 possible options for the numbers. Okay, so in the decimal number we have 10 options. Okay, good. And radix sort uses a couple of stages. Okay, so at each stage we can sort using just 1 digit from MSD to LSD. So let's try this example. We have some numbers here. Okay, first we use the largest, the most significant digit, which is the first digit. Okay, so look at this, 3, 4, 6, 8, 4, 7, 3. And with this digit, we don't care the next 2 digits. Okay, we don't care. So we focus on the first digit, and we distribute all the numbers into the bins. So in this case, we have 10 bins. Okay, compared to these cards. So when we use the cards, we have 4 bins. Okay, and then we put all the cards into 4 bins. Likewise, in this case, we have 10 bins and we distribute all the numbers into one of 10 bins. So this one 3. So we put this number, this key into this bin. Okay, and then this one goes to this bin. This one goes to this one, here and here and here. So this bin has 2 keys and this bin has 2 keys, and this one has 0 keys. This one, they don't have keys. Okay, so it's kind of, based on these distributions, it's kind of half sorted. Not exactly, but half sorted. Look at this one. So these ones are smaller than these ones. Okay, these ones are smaller than this one, smaller than this one, smaller than this one. So it's kind of half sorted. And within these bins, then we have to sort one more time. So in this case, we apply the same principles. So we are looking at the second digit, okay? And we need 10 bins. And we put this number to this bin and this number to this bin. Okay, so in this approach, we need how many bins do we need? So we have 10 bins. We have 10 times 10 bins. Okay, and then we have the next stage. Let's say if we have 3 to 8. Okay, then we have 3 to 8, and we have 3 to 8. We have 2 keys in this bin. Then we need the next stage. So in the next stage, basically, if we have a lot of numbers here, then in the next stage we have 10 times 10 times 10 bins. It means 1,000 bins, 100 bins, 10 bins. So basically 1,110 bins. That's what we need to apply a radix sort for 3-digit numbers. What if we have lots of numbers like 3, 2, 5, 5, 4? So we have 5 digits. What happens? Then we have this many bins, right? So that is a problem. There is overhead to manage lots of bins, and these bins are in the memory space, and we have to handle lots of memory space, and that's kind of the terrible approach in a sense. As I said many times, the memory access is really expensive. If possible, we have to avoid using the memory space. Okay, so if we sort from the most significant digit to the least significant digit, then every time, from this stage, for the first stage, how much computational cost do we need? It's just linear time. Why is that? When we read this number, when we check the first digit, we can put this one into this bin, and we know where the bin is. So just put it in that bin, and putting one key to one bin takes just constant time. Okay, so we need constant time for this key, and we need constant time. So in a bigger notation, it is just a linear time, just n. Okay, for this stage, we need linear time. From this stage to this stage, we need a linear time. Look at this one. We have one key, and we have to put this key into one of the bins, and putting one key to one of this bin takes just constant time again. So we have n keys here, so basically we need n time, so linear time. So we have linear time, and for this stage we need a linear time, and for this stage we need a linear time. So when we have a k digit, then basically it is kn. Okay, that's way much better than quicksort and heap sort. They are like n log n. If n is like 1 million, okay, then k is 6, right? Or it could be 5. But log n, what is log 1 million? if we use binary, then 1 million. But it's way much bigger than 5. Okay. So radix sort is better than quick sort, or merge sort, or heap sort. Yeah, in a bigger notation, it's better than any other sorting algorithms. But in practice, in reality, quick sort is faster than radix sort in many cases, for many cases. Why is that? As I said, radix sort relies on the memory access heavily, and that is a pain. Okay, so because of the memory access, even in the computational cost, it is much smaller than other algorithms, but actually it takes more time. Okay, so when we use the radix sort from the MSD to LSD, then we have lots of bins. Okay, so there is another kind of more efficient approach than this. We can apply a radix sort from LSD to MSD. Okay, it means we sort the keys based on the least significant digit, the last digit. Okay, we focus on the last digit and then we sort, and then we sort the keys based on the second digit and then the first digit. Okay, and there is one important to notice here. The algorithm to sort each digit should be stable. Okay, so I will tell you why it is necessary. So let's try this example. Okay, so first let's sort these keys based on the third digit. So this one is a 0. Okay, let's follow this process one by one. So this is 9. Okay, 9 goes here, and the 7. Okay, the 7 and the 9 and the 6, 0 and 5. It takes just a linear time. Okay, good. But this is stable, so it means for 57 and 657, they don't change the order, even though their key, the digit, they have the same digit, 7 and 7, but they don't change the order. Okay. In this case, accidentally it looks good, but if we have 657 and 457, then still we don't change the order, so it should be 657 and 457. So we shouldn't change the order. Okay. So we just distribute the keys based on the last key, the last digit. Okay, this is the first stage. Okay, in the next stage, and we're gonna look at the second digit. Okay, and then this one is 2. Okay, so we put this one to this bin, and the 5 and the 3 and 5 and 5 and 2 and 3. Okay, so we just used the second digit, and then again we didn't change the order when they have the same digit. Okay, in this case it is 5, and okay, let's look at this one, 720. So the second digit is 2, and this one is 2. So this one is the first one, and this one is the second one in the bin. Okay, we don't change the order. That's important. Okay, we don't change order. And then in the last stage, we focus on the first digit. Okay, and then we have bin 7 and bin 3 and bin 4 and bin 8, bin 3 and 4 and 6. This is sorted, right? Because we didn't change the order. So when we have the same 3 here and here, and we didn't change the order, because the reason why we need a stable sorting algorithms between the stages is that these ones are already sorted in a sense. Okay, so when we distribute these keys to the next stage, even when they have the same key, like 3 and 3, then we shouldn't change the order of these two keys. If we are not sure, so if the sorting algorithm is not stable, like a quick sort, then when we distribute this number and this number to this bin, then we might have different order, like a 3, 55, and 3, 29. Then we are losing some information from these stages. So to keep the information from these stages, then we have to use a stable algorithm. Okay, so in this case, we don't need many bins here. We can use a linked list to implement more efficiently. But in the previous slide, we used lots of bins, but in this approach, we don't need that many bins. Okay, and the complexity is just this. In this case, in the previous slide, we used the K. In this case, D is the same kind of thing. So D is the number of digits. So in this case, 3. Okay, so we don't need many memory space, and the computation cost is way much smaller than other sorting algorithms, but still we need lots of memory access here. So, but this is beautiful in the computational cost, but in theory, we don't know. Okay, now let's compare some sorting algorithms. Okay. On average case, quick sort is kind of fast, and the merge sort and heap sort and insertion sort. But when the number of elements is small, n is the number of elements. So when n is small, then maybe insertion sort might be slightly faster than quick sort, and sometimes merge sort will be fast enough. Heap sort could be, but it doesn't matter. When the n is small, let's say a quick sort, insertion sort might be faster than quick sort when n is small, but it doesn't matter because when n is small, whatever you use is fast enough. So our concern is on the large number. When n is large, then it might take like a couple of minutes. Then it makes some difference. So only when n is large, then we have to be careful to select our sorting algorithm. And again, this is kind of average time. If you think that your list is already kind of sorted, it's almost sorted, then the quick sort should be the last choice. Okay, and maybe insertion sort might be better than other sorting algorithms. Okay, and we can check the preferences of sorting algorithms. Okay, as I said, when n is small, insertion sort is better, and when n is large, then usually on average quick sort is better. But again, it depends on the distribution of the unsorted list. Okay, but as I said, when n is small, it doesn't matter. We don't care. And practically, combining insertion sort and quick sort and merge sort can provide a good performance. But usually, if you are not studying the sorting algorithms, then it doesn't matter. Just if you don't have any idea about the input list, then just use a quick sort. Okay, usually that works.